So today we'll be presenting on the creation and validation of the BYU-Idaho metabolic cost equation. My name is Jake Barchi.
And I'm Brandon Neworth.
So you may be wondering, what is metabolic cost? What does that mean? Metabolic cost is the amount of energy required to perform an action. And in the case of our metabolic cost equation, that action was walking on a treadmill at varying speeds and gradients. Now, metabolic cost can be measured in different terms. It can be measured in kilojoules per minute. It can be measured most commonly in calories. And in the case of our equation, it can be measured in oxygen consumed in milliliters per kilogram of body weight per minute of exercise, and this can then be converted into calories. Calorie tracking is something that has become increasingly popular nowadays for those that exercise. You go to the gym, you want to know how many calories you burned on the treadmill. You go to the gym, you want to know how many calories you burned weightlifting, right? Even people have tracking devices that they can wear on their wrists, like Fitbit and Garmin. The popularity has increased significantly in recent years. Through research, we were able to discover metabolic cost equations that have been validated and developed in the past. Perhaps the most prevalent is the American College of Sports Medicine equation, the Pandolf equation, and the Manetti equation. Through further research, we found that there have been other researchers who have investigated the accuracy of these equations, and it has been found that there are inaccuracies involving the American College of Sports Medicine equation and the Pandolf equation. The American College of Sports Medicine equation was found to have a standard error of the estimate as high as 13.2% of the mean, and the Pandolf equation as high as 15.8% of the mean, while the Manetti equation has not been compared or investigated thoroughly. For this purpose, we created the BYU-Idaho metabolic cost equation to provide a more accurate metabolic cost equation. So for our methods, we collected two data sets. The first data set was labeled as our training data, and it consisted of 57 subjects, both male and females. Each subject walked on the treadmill at speeds of 1, 2, and 3 miles per hour, and also at grades ranging from negative 18% grade to positive 40% grade. Each subject started at negative 18% grade, then negative 15% grade, and progressed up to positive 40% grade in increments of 5% grade. And each subject was allowed to rest for 1 to 10 minutes depending on the subject's needs between each trial. And respiratory exchange ratios were gathered through the use of indirect calorimetry measurements, which measure the oxygen uptake and also carbon dioxide production. And through the ratio of carbon dioxide to oxygen, we get our respiratory exchange ratio. And respiratory exchange ratios above 1.0 and above were not included in the training data set to ensure that steady state exercise had been achieved. For this purpose, we created our equation for steady state exercise and not strenuous exercise per se.
This is called the training data set because we used it to create our model. So first we looked at a pairs plot, which compares all of the variables that were collected. And we looked at several of them, including heart rate and BMI, but we found that grade and speed were the significant ones. So we created our model based off of those.
The second data set that we collected was labeled as the validation data set, and it consisted of 91 subjects, this time both male and females, and each subject walked on the treadmill at speeds ranging from 1 to 3 miles per hour, and each subject walked in 3 different percent grade categories. The first category was negative 18% to 0%, then 0% to 12%, then 12% to positive 40% grade. Each subject completed a total of 3 trials. One trial was completed in the negative 18% to 0% category for a total of 5 minutes. And then in the 0% to 12% category for an additional 5 minutes. And then the last trial was completed in the 12% to 40% category for 6 minutes. And each subject was allowed to rest as long as they needed to between sets. The trials lasted for 5 or 6 minutes to ensure that steady state exercise had been achieved, and again, respiratory exchange ratios exceeding one or higher were not included in the validation data set.
So this is the data set that we used to validate our model off of so that we could see how accurate it was in predicting metabolic cost. We also used it to compare our equation to the other equations in research. So this is our model that we have found, and like I said before, the significant variables are grade and speed, and we found that their interactions as well as going up to cubing grade were significant, as you can see from the p-values on the right side of this table. We also found that the adjusted R-squared, which is the proportion of the variation that is explained for metabolic cost, and ours was 0.89, which means that about 89% of the variation of metabolic cost is explained by grade and speed. This is the results that we found when we validated our model. So we took the adjusted R-squared for each equation because instead of using regular R-squared, we used adjusted because it takes into account the amount of variables in each equation. And we found that ours in this data set is 0.83, which is slightly lower but still very good. And the only one that was higher was Pandolf at 0.85, but they are so similar in their adjusted R-squares that they are pretty much on par in their accuracy.
As Brianna said, the BYU-Idaho metabolic cost equation was the most accurate equation across the entire range tested, which was negative 18% grade to positive 40% grade, and speeds from 1 to 3 miles per hour. This is significant because other equations, as mentioned, the Pandolf and the American College of Sports Medicine equation only take into account gradients that are positive. And the American College of Sports Medicine equation was validated for speeds of 1.9 miles per hour to 3.9 miles per hour, and the Pandolf equation was validated for speeds ranging from 1.5 miles per hour to 4 miles per hour, as well as the Minetti equation. Now, the Minetti equation also accounts for positive and negative gradients, but was found significantly less accurate than the BYU-Idaho metabolic cost equation. Something else to note is that the BYU-Idaho metabolic cost equation had the lowest total error in comparison to the other equations of ACSM, Pandolf, and Minetti. So what next? The BYU-Idaho metabolic cost equation was accurate in predicting VO2 levels and, in essence, energy expenditure. And it was more accurate in our range of gradients and speeds than any other equation that has been validated up until now. Well, that is a great achievement. We believe that we can make the equation even more accurate through further testing. We have planned to recruit 10 more subjects to walk at higher speeds and higher gradients, speeds ranging from 2 to 3 miles per hour and gradients exceeding 20% grade to further to make our equation even more accurate.
So these graphs represent the spread of data that is taken into account for in our equation. This is the training data, and as you can see, there is a fair spread, although there is some missing here where it is still represented in the whole equation. However, in the validation data, you can see that the square on the far right is empty, and so the data is not fairly represented throughout the entire spread.
And through further testing with these 10 subjects, we would be able to more accurately portray the original estimation equation and improve our total error and our R-squared value.